This is BBC One. And now, the computer programme.
2 trout got them. Milk got that. 2 ounces of seasoned flour, 2 ounces of butter. And that's the problem. My scales only read in grams, so I need to summon my instant conversion tables. Like this. Imperial metric conversion program. Enter imperial units. We're going to enter ounces. How many ounces do you want? 2. 56 grams. Easy as that. Now, all that, the recipe and the instant conversion tables, are being taken from the BBC's CFAX service by the home computer in this kitchen. In fact, you may not realise it, but I'm surrounded by computers in here. There's one in my washing machine, there's one in the cooker, one in the central heating controller over here. There's even one in the toaster. In fact, most of the computers we'll all be coming across in the future will be built into the equipment itself. But though we may not see them, it will be the computers which are in control.
Imagine you're lost in an alien world of high walls and mysterious passages. Could you find your way with only a sense of touch and a perfect memory for where you'd been? If a machine can find its way around this maze, could it also be engineered to solve the problem of manoeuvring its way through your living room and hoovering the carpet? Perhaps the mighty Thumper could. He's the champion of the Euromouse maze-solving contest.
3, 2, 1, go! And here is Sterling Mouse, up till now the champion. After a tremendous performance in Paris, now what is Sterling going to achieve this time?
Every year, the final draws enthusiasts to London from all over Europe.
Oh dear, that's where the maze is a bit tight.
When they arrive, the only thing the mice know about the maze is that it's square.
It knows where the middle of the maze is, but it doesn't know what's in the way. It's got to learn where the maze is. It's got to analyse that maze, working out what the shortest path is, going back, having a better try when it's found out a bit more. That really is the essence of robotics. 3, 2, 1, go! It's a lively mover.
Some of the mice at this event don't seem quite to have got the hang of it.
I think you might be well advised to sort of lift out and restart. The time now is running out rather fast for qualifying, so if we have any other mice who would like to qualify, which other mice have not yet qualified?
Of the 20 entrants who brought their mice here, only 3 managed to reach the centre. Many didn't even get as far as the starting gate.
That's purple, isn't it? No, it's red. We've got to swap red with brown.
All the enthusiasm in the world couldn't get some of them working in time, but you can see that the technology is capable of building a machine that could hoover your carpet, or even mow your lawn, or not, as the case may be.
Do you want to do it again to check they didn't come on? Because it might be a fault in the analogue board, you see. Brake light, is that the brake light?
Yeah.
One,
there and down.
Yeah,
3, 2,
down,
1, go! Now that's a nice bit of movement, but tell me, what's your algorithm for finding the centre of this maze?
I think it's willpower, actually.
Well, there he is just going into a lobster pot. Do you really think Questa's going to come out of there?
Well,
It's always possible.
Given enough time.
Questa will only escape from its lobster pot if it's lucky and happens to be pointing in the right direction. Questa's designer has given it no memory yet to remember where it's been. It only has the power to go forwards. It almost looks like instinct, not to say optimism. Whatever obstacles it meets, it changes direction, but still keeps trying to go forwards. But what happens if you give one of these mice a memory?
Well, let's see how long it takes him to the middle.
Can a mouse like Theseus, for instance, which seems to know its way around the maze, be considered intelligent?
No, it's absolutely dim. This particular mouse has a program which will, I hope, solve one particular problem. Outside of that environment, it's useless. He's only following a set of instructions that I told him to do. If I give him wrong instructions, he looks very stupid indeed, because he goes down the wrong path.
Well, here he is, Theseus, the amazing maze-learning micro mouse. Now, the program has two quite separate functions. I'll really show you. Take off the mouse part. Sorry, old chap. One controls its physical position by sensing the walls of the maze through these little whiskers all the way around, and driving the little motors, which in turn drive the wheels. And the other works out where the device is in the maze and navigates it to the centre by the shortest possible route. The whole operation is controlled by an ordinary low-cost microcomputer, the sort you can buy in the high street. And I can prove just how normal it is by making it look like the micro we know and love. All I have to do is plug in the keyboard and plug in the television, and in fact, in completely the ordinary way, we can list the program, and there it is on the TV screen. And that's the program that makes Theseus such a terrific navigator. Now, Mac, the actual mechanics of it are those little metal whiskers, which are like a real mouse's whiskers, sort of detecting where the walls are and switching motors on and off, is that right?
Yes, and also sending signals to the computer, which are, again, on-off signals when it detects the end of a wall, so the computer can form the maze.
So there's a lot of switching going on.
That's right. And I can show you some switching here. If you take this ordinary little calculator with a liquid crystal display, though each of those numbers has 7 possible positions that can be illuminated.
Yeah.
And by various combinations of these 7 possible positions, you can form each number, each character from 0 to 9.
I've seen those many times. I've often wondered how they were done.
Well, you can see it better on this one. You can see this is the outline,
yes.
And as we go through it, it sends a signal down one part here to illuminate that, down this wire to illuminate that, and is effectively 7 switches, just like ordinary light switches, you can almost imagine them.
Yeah.
And it will go around and do any one of those 7 different things. So by any combination of these, you can do a 2, or a 3, a 4, 5, 6, 7, 8,
And
9.
each time, it's a combination of these connections.
Right, on, off, on, gives you that series. Of course, we're not using all of them, and you can get some curious combinations, like that, for example, which is quite meaningless, but that's one of these 3 connections, and it's quite meaningless.
That's terrific. Well, by acting as a highly sophisticated switch like that, a computer can control a washing machine, for example, opening a valve to let water in at one moment, then turning on the heater, revolving the drum, at the same time measuring the temperature, sensing the water level, and so on. Now, although computers can be very small, there's no limit to the size of operation they can control. Jill Neville found one which will take your breath away.
The way we treat our sewage has changed little in the last 100 years. The effluent is fed into large tanks where the solids settle out at the beginning of a process that seems largely automatic. But hidden beneath the surface are the real scavengers.
Nature has a key role to play in the purification process. After the indigestible solids have been removed, tiny microorganisms in the tank break down the polluting chemicals into harmless constituents. But to do their work, they need oxygen.
After only 12 hours, this army of unpaid workers has produced an end product pure enough to pour straight into the nearest river or sea. But it's this purification process that engineers are now trying to optimize.
To make the purification process even cheaper, we need to make it more efficient, and that means getting the best out of the bugs. At the moment, for example, they're fed the sewage as and when it's produced by the supplier. But would they process it more efficiently if it were fed to them at a constant rate?
Because you can't ask bacteria directly, you have to resort to experiment. Next to these tanks, engineers from the local polytechnic have built an experimental sewage plant. At its heart is a small computer controlling the environment of those tiny microorganisms and monitoring everything they do.
When it rains, the sewage becomes very dilute, and those bugs could go very hungry. But sewage, being what it is, you can't use a valve to monitor the rate of flow. So the computer issues instructions to this motor to drive the thread and lower a floppy pipe.
But you can't just connect a floppy pipe to a computer. The pipe and its motor are part of an analogue world of continuously changing flow rates and fluid levels, while the computer can only handle electrical signals, digital patterns of ons and offs. To bring these two worlds together, the analogue signals must be converted by expensive interface units to those on-off patterns. In comparison, the computer the engineers have chosen is cheap and almost inconspicuous. To change the rate of flow and so alter the nourishment level for those bugs, the computer can divert sewage to and from a balance tank. This enriches or modifies the food supply, which the tiny microorganisms thrive on. But the efficiency with which they break down the sewage can only be measured by another expensive piece of apparatus, a total organic carbon content analyzer. Researchers in Portsmouth hope for huge financial savings if they can process more sewage faster without a drop in the quality of the end product, or by having a clearer understanding of those tiny microorganisms.
By monitoring every aspect of the bug's environment, the scientists hope soon to discover what suits them best. Perhaps, like us, it'll turn out that they like their food at fixed meal times, with pauses in between for digestion. But whatever happens, that high-street computer in there has the flexibility to handle it.
A personal computer providing a real public convenience. Now, a number of the computers we've seen at work so far have had the ability to do more than one thing at a time. Now, Mac, is that something it's easy for a computer to do?
Well, it's quite tricky to program that because the computer itself can only do one instruction after another. Of course, it works very, very quickly, so it just seems to be doing lots of things at the same time. For example, it might be reading the temperature and adjusting a heater. It might be reading water flow and adjusting a valve. In fact, some of the larger computers, you can have many programmers actually sitting down programming on them, and they don't know if anybody else is on the system at all. They're called time-sharing systems. Think of yourself as a waiter, and a well-organised waiter. He will be taking the order from one customer whilst another customer is actually eating his food, so each customer believes he's got one personal waiter. If you keep going at that speed, Chris, you've got a job for life.
Getting a computer to share its time between a number of different tasks is obviously a complicated thing to do. But how does a computer actually control anything, Mac?
Well, we can show you on this micro, a very simple little program. What we're going to do is to improve the comfort in your living room. And we've got a heater here for when the temperature drops below a certain level. Yeah. And we've got a fan here for when the temperature is higher than a certain level to give you real creature comfort. We've got a temperature sensing device there.
Yes.
And a piece of wire which will feed into the back of the computer. And we've written a little program which is here.
We can actually do that.
Yes, we can do it.
Now, 100 temp for temperature, I guess, equals add val 1. Well, you've lost me straight away with the first line.
Well, that's very simple. The value that we're putting in here of the temperature in centigrade, we're inputting through port number 1 in the back of the computer. So we get into the computer the actual temperature in centigrade, and we're going to call it temp.
And add val is something that the basic language that the computer understands.
That understands, yes.
It's expecting a value, all right. Now, those chevron signs are something I remember from my long-forgotten maths. If temperature is more than 25 degrees, I assume, then proc switch 1.
Well, this is a procedure, and we've given this one the name switch. So in this case, we've said procedure switch, go to procedure switch, and the switch is a 3-position switch, and set it in position 1. Now, what that will do, it will send a signal down this wire from the computer into this isolation box, which isolates it from the mains, and then it will switch on this fan, because it's greater than 25 degrees, and switch off your fan heater if it happened to be on.
OK. Well, that makes the next two instructions very straightforward in that case. If the temperature is less than 15, then proc switch 2. That's the other wire controlling the other thing. If the temperature is more than 15 and the temperature is less than 25, then proc switch 0. What does that mean?
Well, that means switch them both off. If it's between 15 and 25, you don't want a heater, you don't want your fan, so it simply switches them both off.
OK. Can we make it go?
Yes, let's run. Oh, well, I'd heat that up first, because nothing will happen because we're between 15 and 25 if you make it nice.
We are, you're right. 22, the studio temperature, 22.2.
Right.
Let's wham it up to something that... Oh, God, that was quick. 50. That should do it. R-U-N, return. And
there goes the fan.
Magic. Wonderful. Now, I've got some cooling spray here. I'm just going to see if it goes off. Nothing's happened.
No, it won't, because the program isn't running. It's run through once, which is enough to set this going, but it's not running anymore.
Oh,
it's
I
done
see.
its job.
Once and for all program. That's all we've done.
But we've got to convert into one that runs continuously. It's continuously sensing the temperature.
So we have to put in another instruction.
That's right.
It's going to be 140. That much I can manage.
Well, what you want to do is to go back to the beginning. Go back to this first instruction, instruction 100.
Well, there's bound to be a basic computer jargon expression for that.
Go to.
Oh, just that?
Simple as
Go
that.
to...
Go to 100.
Oh, I see. That's in one word, isn't it? Go to.
100. And run. Return and run.
Well, the fan's stopped. That's very good. No.
So we must be between the two.
Yes, we are. 17 point something or other. Let's just quickly cool it.
There we go.
And the fan heater comes on. That's very good.
It really works.
That's terrific. One thing that does occur to me, Mac, is that it's normally the sort of job that you do with a very cheap thermostat on the wall. You know, you don't need a computer to turn your central heating on and off, do you?
Well, this is a general-purpose computer, and obviously there's not more chips in here than you, strictly speaking, need to control the heat in your room. For example, there's a chip to control the screen, and you wouldn't need the screen. There's a chip controlling the keyboard, and you've got chips controlling the disc. We've got chips controlling the cassette recorder, and so on and so forth.
Yeah.
So if you took out the ones we really needed, you'd have something like this, which is a processor, some memory, and something to handle the input-output.
Right.
So you end up with 4 chips. But even so, you wouldn't have 4 chips. You'd get that all into one single chip, and a special chip will be produced.
Right. Well, it's difficult to imagine the scale on which the electronic circuits are working inside that chip. I mean, as we've said before, the instructions and information are stored in little electrical ons and offs. Well, we can demonstrate the physical size of each one of those circuits with this American stamp. If we could zoom in onto the map so that we could see every state, every town, and then close right down to every street, and then every house, that's the scale of the detail that's photographically etched onto the silicon. And these are some of the connections on the chip. And this is the whole circuit that makes up the kind of area of the chip. And this is the chip itself. In fact, the total area on that chip is about 1/4 of an inch square. How on earth, Mac, do they get all that onto something that size?
Well, the principles are fairly straightforward. If you take your holiday snaps and a piece of 110 film, they're about that size, and you send them off and get them developed and then enlarged, and you get something back like this. Well, this, in principle, is what they do in reverse. They draw out a circuit as big as this, and then they photo-reduce a set of these so small that they can be used to etch the components and the circuits on a tiny piece of silicon. The great thing is you can produce them that will do many different things. The same chip can be used to run your toaster, that can run your washing machine, that can run your dryer, and so on. And because the programs are only set in the thing right at the last bit of manufacture.
Oh, I see. So they're all more or less the same design until you just get to the last stage where some extra sort of doorways, some doors are opened and other doors are closed to give it its specialist function. So
exactly right. So that they go, but once they've made one chip, they can make it very, very cheaply.
So how much is that?
Well, I don't know. They're between £1 and £5 usually.
Is that all?
Yes.
It's extraordinary, isn't it? Because the computer in a chip is so fabulously cheap and so reliable. Many domestic gadgets now use them, as Max said, instead of the old electric motors and relays they used to have. This washing machine controller, for example, I mean, it's an easily recognizable thing. Set your washing program on that and then leave it to quietly tick away to itself. Actually, let me show you. We took one to pieces just before the program, just to see what it contained, and there's an awful lot to go wrong there. Now that has been replaced by this. Computer chips on a board, doing exactly the same job, with no moving parts, almost total reliability, and the capacity for lots more functions. Fresh uses for this kind of electronics are being dreamt up all the time, as the advertisers go to great lengths to tell us.
And these advertisers don't hesitate to use glamorous TV commercials to paint vivid pictures of an amazing and perhaps a little bit unbelievable computer-controlled future.
The motor car is likely to become the biggest user of the silicon chip outside the computer industry. We're already being seduced by a glossy image of life with microcomputers. Step inside and sit at the seat of a car that's so full of microcomputers that a driver hardly seems necessary. I once bought a car where, to maximise engine life, the instructions were to change the oil every 1,500 miles if it was in heavy usage, i.e. you were driving it in heavy traffic. In medium usage, you change every 3,000 miles, and light usage, cruising up and down motorways, you change the oil every 6,000 miles. The trouble was, I could never remember exactly what I'd used my car for during the previous period, so I used to change the oil whenever I thought it needed it. Well, happily, the problem has been solved. We're now able to measure every possible thing that this car is doing in its engine. And by using electronic sensors, we can take the oil temperature, the oil pressure, the engine revs, things we've been doing for years, but in addition to that, to take fuel flow, how much fuel is being used, how often the car's being used, how long the journeys are, the number of times the accelerator's been pressed, and for how long.
No matter how this car is driven, information from the sensors builds up a picture that can tell me when it needs an oil change or a service.
And that is the secret. A single-chip microcomputer system that carries out all this work. Well, I could imagine that this could actually save the life of your engine, but there are other microcomputers in this car that could save your life.
In an emergency, a computer takes over and stops the brakes locking. You can brake and steer without losing control.
This time, the sensors measure the speed of each wheel and feed the information to a microcomputer controlling the braking circuits. Just before the wheel locks, the brakes are released for just a fraction of a second.
There are actually 6 computers in this car, each one dedicated to a separate task. Providing information, controlling your safety, and if you keep an eye on your fuel consumption indicator, you could cut your petrol bills.
The microprocessors in this car are not of themselves particularly expensive, so we're likely to find them on much cheaper models of the next generation. But it's not just in motor cars we're going to find them. Wherever we want to be in better command of the environment that's surrounding us, whether it's for better comfort, safety, security, or economy, then we're going to find it's the chip that's in control.